So we're gonna get started. Wow. First of all, there's a lot of people there. Thanks for coming. Sorry if you had to cram your way in at the end there, but we're I think we're maybe beyond the fire code. So, my name is Joe Condruccio. I help to co-organize the group with Gideon, who's at the back there. So I sort of have two roles to play tonight. So the first one is welcome to Boston Machine Learning. We're going to have a talk on TensorFlow tonight. The group now has almost 4,000 members, which is insane. And we have talks basically lined up through December, so keep an eye out on the meetup page. The next thing to do is welcome to Spotify. I'm a machine learning engineer at Spotify. We're really happy to have Boston Machine Learning here. If you are from Spotify, can you raise your hand? Okay, so they're hiding in the back. Surprise, we have an office in Boston. Actually, it's not real. And we are hiring machine learning engineers, data analysts. So if you're interested in any of that sort of stuff, come find somebody with like Spotify something. And let me turn it over to Nathan, who's going to start us off with attention.
All right, thank you so much for coming. So my name is Nathan Lintz. I'm a researcher at Decoder Data Solutions, and it's a big part of my job. I write TensorFlow models. In today's talk, we're going to be talking about how to write some basic models in TensorFlow, some common tips and tricks to avoid pitfalls when building your own models in TensorFlow. And we're going to actually move on to building recurrent neural networks from scratch in TensorFlow for the task of image generation. Before I continue, is the volume good? You guys all hear all right? All right, great. So, building models in TensorFlow and perhaps machine learning more broadly is a lot like baking a cake. You might start off with some delicious batter. Perhaps you'll put it in an oven. And since we're just baking the cake for the first time, I'm not really sure what the temperatures should be. So perhaps we set it to like 500 degrees. Let's see what the result is. Cake came out on fire. Whole house burns down. Not the right temperature. So back to the drawing board. We shift the temperature down, maybe like 200 degrees. Let's see how we're doing. Oh, undercooked, mushy, globby mess. So from these two kinds of data points, we know that we have to adjust the temperature somewhere in the middle. So we're going to try that, and out comes a beautiful cake. So how does this relate to machine learning? Well, in any sort of machine learning model, you have your inputs, which is like our cake batter. You have your parameters and operations. The parameter might be something like the temperature, and the operation would be like, putting it in the oven, baking it. And then you have your outputs, and that is the cake that comes out. But there's a key part that's missing in this diagram. Now remember, when the cake came out on fire, we were really sad, and we knew that since the cake was like too hot, we had to decrease the temperature. And likewise, when the cake came out just right, we're happy, and we know the temperature parameter is set about right, so we really are able to build in this feedback loop where we can adjust our parameters iteratively based on the outputs of our model. So let's add that to our diagram. All right, great. So here we see we have our inputs, we have our parameters and our operations, and we have our outputs. And we also have this little feedback loop where, based on our outputs, we're able to compute some sort of cost, maybe the cost of like repairing the house after it burns down, and we can update our parameters accordingly. So we're all scientists here, and when we're trying to build these kinds of models, the most important part is collecting the data. So here is some data points that we might have collected if we were trying to model the relationship between the temperature that we set and the doneness of the cake. When the temperature was too low, the cake comes out mushy and gross. When it's too high, the cake comes out burnt. And somewhere in the middle, it's just about right. And if we notice about how these data points are arranged, perhaps it might, fit a line. So let's say that the model we're trying to use in order to fit this sort of data would be a simple linear model. Y equals mx plus b, standard equation of a line. We might call this kind of task a linear regression, where we're trying to fit our data points to some line and that way we can then later make inferences about what the appropriate temperature should be for a given doneness of our cake. So in the context of the diagrams earlier, M and B kind of represent our parameters that are associated with baking, and adding mx to b is like our operation, and our output is our y-axis, which is our doneness readings. So let's jump back real quick. Here we see our graphical model. We have our inputs again. You might call that x, and y equals mx plus b. You have your parameters and ops. That's your m and your b. And then you have your output. We'll call that our y value, and that's our prediction. And to add a little bit of TensorFlow nomenclature, whenever we're going to be feeding some sort of data into our model, we need what's called placeholders. And these are just areas where you can literally just take your data points and feed them into your model and get some sort of prediction out. So when we're computing our cost function, since we have points for what our doneness readings were, we're going to treat those as placeholders because we want to fit our line to the doneness we've collected. And our inputs, our x values, or the temperature readings, are likewise going to be placeholders. Now, before we actually dive into code, let's just remember the 5 easy pieces of building any sort of TensorFlow model. The first is your placeholders. Again, this is where we feed data into our model. The second is our parameters and operations. This is really like the heart of the model. It's where you set up the values like the m's and the b's, and you kind of define the equations that you're trying to fit. Then we have our cost function. So in the context of baking a cake, it's like the cost of having a ruined cake or having the correct cake, or in the case of our line fitting problem, it's the cost of having the incorrect line fitting to our data. Next, we have the optimization step, and that's a step where we take our cost function and we iteratively update the parameters based on however, the cost tells our parameters to move. So if the cost is too high, it will tell the parameters to move in a direction such that our costs will be minimized. And finally, the fifth easy piece is our training code. And the training code is simply the loop where we take in the data we've collected, we pass it into our model, and we run the optimizer step time after time in order to ideally minimize the cost and have the optimal parameters for the system we're trying to model. So let's hop into some code. All right, so this is our first easy piece. This is the inputs, or the placeholders, where we're going to be passing data into our model. So in the first line, I simply import TensorFlow. After that, I define 2 placeholders. One of the placeholders corresponds to the temperature readings that we collected. And to define a placeholder, you simply need to call tf.placeholder. You pass in a type, and these are going to be floating point values. And then you have to pass in a shape. The reason I chose 10 by 1 is because I had 10 temperature readings, and each temperature reading is a scalar temperature value. So 10 for the number of examples, and 1 for the shape of each example. Likewise, the cake doneness, or the y values that we collected, are also going to be a placeholder. They're also floating point values. And again, we have 10 examples, and each example is a scalar doneness reading. The second easy piece is our parameters and operations. So again, this is going to be where we compute mx plus b to fit the line to our data. So for the m variable, I simply have to call tf.getVariable. I'm going to give it a name, temp_m. I'm going to give it a shape. I give it the shape 1 by 1 because we're mapping a scalar temperature value to a scalar doneness value. Likewise, we define a b value for the b component in our mx plus b equation in much of the same way. And then to get our output, or our y, what the prediction of the model is, I simply have to call mx plus b, and TensorFlow has an mx plus b module built in. That's where you see the tf.nn.xw plus b. And the parameters of this function take in the x value, which is our temperature, the m value, which is the m parameter that we define, and the b value. Okay, let's move on to the next easy piece, which is our cost function. So the cost function is how we know to update our model based on how inaccurate it is at modeling the data we're feeding in. So since we're doing a linear regression, we're trying to fit a line to some data points, our cost function is going to be mean squared error, where we take the cake doneness, and that is the y value that we collected. We subtract from it the predicted y value, take the square, and simply take the mean. Next up, we're going to be talking about the optimizer component. This is the fourth easy piece. And in TensorFlow, they have a bunch of optimizers built in. So here we see the gradient descent optimizer. And this will simply walk the graph of our cost function down, trying to iteratively minimize it. And in order to set up this object, we just have to give it a learning rate, and that will control how fast it will learn. And then we have to tell it to minimize the cost. So now TensorFlow behind the scenes is going to look at what our predictions are, what the y values that we collected were, compute the error, and know how to minimize the parameters of our model in order to have the smallest error possible. And now we're going to look at the actual code we use to train this model. So this is the last easy piece. So the first step is we construct a session object, and the session objects simply allow you to run different parts of your TensorFlow model. And I didn't want to really burn down my house, so instead of using like data points I actually collected, I simply created some data points in NumPy. For our temperature readings, I have 10 data points arranged in a line, and for the doneness, I multiplied the data points by 5. So 5 is our expected m value. I added 1, so that would be like our b value. And I added a little bit of random noise, just so that way the points didn't fit on a perfect line. Then, for 100 iterations, I tell TensorFlow to run the optimizer, and I feed in the temperature values and the doneness values. And ideally, after we run this for enough iterations, the linear regression will be fully trained, and we can begin making predictions out of it. So to do that, I tell the session to run our prediction op, which is the mx plus b, and I just feed it the training data that we used when we were optimizing. So let's remind ourselves, we just defined the TensorFlow 5 easy pieces. There's the placeholders, that's the x and y values that correspond to the data we collected. There's the parameters and operations. Those are the m and b values and the mx plus b equation that we defined earlier. We have our cost function, which we defined as mean squared error. We have our optimizer, where we're using gradient descent. And finally, we have our train code, where for 100 iterations, we're feeding in the data we generated and minimizing the cost in order to find the optimal parameters. So let's see how we did. Okay, so remember, we said our equation we're trying to fit is y equals mx plus b. When I ran the optimizer, it said that m was 4.99, and I set it to 5 initially, so that makes sense. And it found out that b was about 1.21. I set it to 1, so that's pretty close. And if you account for the random noise we added in, these values seem pretty reasonable, and it appears that we have been able to fit a line and create our cake doneness temperature model. So this is pretty cool. We now have a way to map a given temperature value to a scalar doneness value. But the thing is, not all problems really follow the format of a linear regression. Sometimes it doesn't matter what the range of the output values are. We don't care, if it's like 0 or 1 or 5. All we really care about is answering like a yes or no question. So suppose, for an example, we were to ask instead of what is the doneness of the cake, rather, is the cake done, yes or no? So this is no longer a linear regression task, but this would be more like a classification task, perhaps a logistic regression task. So ideally, our model should output a 0 if it thinks the input data should be false, or a 1 if it thinks the input data shall map to true. And while baking is super cool, this example is kind of like a toy problem that we just solved. So let's try to solve something a bit more realistic. A good example would be something like optical character recognition. I'm fed in images of different characters, and the task of the model is to predict what character that image corresponds to. So a really good canonical example of a character recognition problem is something like MNIST. Here's what digits from MNIST look like. On the left side, we see our inputs. There are these 28 by 28 handwritten digit images. So here we see something that looks a little bit like a squiggly 6, and the classifier has to figure out which number it is. So you can kind of think of this as like a multi-way binary classification problem. The models sees this squiggly 6 and has to answer the question, is this a 1? Yes or no? Is this a 2? Yes or no? Is it a 6? Yes. So let's take a little look at what a graphic of a model like this, might look like. So as you notice, it's pretty similar to the gate graphic. Here we have our inputs, our x values, and since each image came in as a 28 by 28 pixel image, if I were to flatten that out, it would have 784 pixels. So that's the dimensionality of our inputs. Then we feed it into our standard mx plus b. But remember, if we just use mx plus b, we're solving a linear regression task. And instead, we want to solve a classification task. So we have to apply an additional operation called softmax, which will essentially crush the full domain of the numbers into something that's like a 0 or 1 prediction. And that will give us the prediction of our model. Then we take in our y true values, and those would be like the labels of what each of the images actually are. So like a 6, an image of a 6 should be labeled as a 6. And those are 10-dimensional because there are 10 possible values for each digit, 0 through 9. So let's remind ourselves of the 5 easy pieces we're going to go through to build this model. We're first going to define our placeholders, then we're going to build the parameters and operations, then we're going to define our cost function, then we're going to create an optimizer in order to minimize the cost and make our model as accurate as possible. And lastly, we're going to iteratively run examples through the model and ideally create an accurate predictor. So here's kind of what our placeholder code looks like. At the top, we import TensorFlow, just like before. And TensorFlow actually has MNIST built into it. So instead of collecting our own handwritten digit data set, we can use the built-in one. And for our placeholders, we need our x values, which are the flattened out images. Again, they're going to be floating point values. I chose 128 as my batch size. That essentially means we're going to be feeding in 128 digits at a time. And again, each digit is 28 by 28 pixels. So we flatten that out, it's 784 pixels. And now we have our y placeholder, and that is what the label of each of the image actually is. Again, 128 because we'll be doing 128 examples at a time, and 10 because each digit could take on one of 10 possible values. So here is the parameters and operations, the real heart of the model. Looks pretty similar as before. We're going to be taking our m parameter and our b parameter. M is going to be 784 by 10 because it takes in 784 pixel input and maps it to a 10-dimensional digit value. And our prediction, again, is going to be our mx plus b using the built-in tf xw plus b operation. The next part of our model is going to be the cost function. So for the cost function, if you remember before, we used mean squared error, but that's really only for fitting linear regression problems. What we're trying to do here is a classification problem, so we actually need to be using softmax cross entropy. And I'm not really gonna have time to go into exactly what that is, but you can look it up later. It essentially is the appropriate cost function for a multi-class classification problem. Now we have our next easy piece, which is our optimizer. The optimizer code looks almost identical to how it was before. Essentially, we define our gradient descent optimizer, we set the learning rate, and we say, go ahead and minimize our cost, make our model as accurate. Is our train code, where again, we construct a session object, and for 2,000 iterations, I grab out a batch of MNIST digits, and I simply run my optimizer, feeding in the digits and the appropriate labels. So this seemed pretty easy, not too many lines of code. The question is, what's our accuracy? Well, if you were to randomly guess what the correct digit value is, it's a 10-way classification problem, so you'd get about 10% accuracy. And this model is getting 92% accuracy. So that seems pretty good. We're able to reduce the error by a huge margin, and 9 out of 10 times we are taking a handwritten digit like a squiggly 2, and we're able to map it to the correct digit. So let's look at some of the examples it's getting correct. On the left side, we see the input MNIST digits. So we see like a handwritten 7, a handwritten 2, and our model is able to accurately classify them as 7 and 2. And that's pretty impressive. Now let's look at some of the examples it's getting wrong. On the top here, we see a digit. I'm not exactly sure what the digit was supposed to be. It doesn't really not look like a 6 to me, but I suppose the model can't be perfect. It didn't realize that that monstrosity was actually not supposed to be a 6. So it's an error, but who knows. And the other ones it's getting wrong are perhaps a little bit more interesting. It thinks the 4 is a 6, thinks the 3 is a 2. But when you dive in, you see that the model is really not that confident about its predictions. Like for example, the 6 to 2 on the bottom, it was only 28% sure that that was a 2. So really what's happening is it's not that the model is just absolutely guessing wrong, it's just not really sure what this image is. It's totally confused, and that's why it's making inaccurate predictions. So how might we solve this? Well, the first model we defined was a logistic regression. We're feeding in examples, we're squashing them down to binary outputs, we're using that as our prediction. We can kick it up a notch by turning it into a neural network by adding hidden layers. This is an example of pretty standard hidden layer for these kinds of models. We, just as before, have an M and a B parameter. You get in some input, and you apply mx plus b, and you return some output. But before returning that output, you have to apply a nonlinearity. And this is really important because if you don't apply a nonlinearity, you don't get any advantage of adding layers to your model. This is because a sequence of linear operations can really just be represented as a single linear operation, whereas a sequence of nonlinear operations actually add additional complexity to what we're trying to build. And a good way to think about this, about nonlinearities, is it's kind of like solving a Rubik's Cube. You have these 6 different faces, you flip the different faces around, really just giving you 6 possible operations you can do. And that would be like a linear system where we're pretty constrained what sorts of things we can represent with a linear function. Whereas a nonlinearity is kind of like solving a Rubik's Cube in Little Brother mode, where you smash the Rubik's Cube apart and rebuild it. Essentially it allows you to map all of your input data to some sort of space that a simple linear function can't operate on, and then the resulting output of that can then be classified more easily. Now the question is, what's a good nonlinearity for us to apply here? I'm partial to the ReLU function, and what ReLU is it takes in a value x and it returns x if x is greater than 0. Otherwise, it returns a 0. And the question is, why is this a good nonlinearity to use? A big reason is because we were seeing that we could get 92% accuracy with our simple model that only had a single kind of linear operation followed by a softmax. So we know that these linear systems are pretty good. So we want to make sure that we still have a linear regime that our model can operate on, and that's the x greater than 0 regime. But in order to add complexity to our model, we have to have a nonlinear regime. So by having the 0 part of our model, the 0 part of the ReLU, we turn this into a nonlinearity that our function can use to essentially build up hidden layers. So let's see what a model might look like if we add in a hidden layer. So in this diagram, it looks kind of like the one from before, but we have a hidden layer. We still have our inputs, and they're still 784 pixel values. But now we have our hidden layer, where we have our mx plus b that we apply ReLU to, and it has its own set of parameters, m0 and b0. And then we have the same kind of classifier layer that we built up in the last example. And that has its own set of parameters, m1 and b1. And the output of that is simply the softmax of m1 times the result from the hidden layer plus b1. And that gives us our prediction. And what I'd really like to call out here is that the only distinction between this model and the model we had previously is this additional hidden layer. If we remove that layer, it would be the exact same model as before, but the hidden layer gives us added complexity and more modeling capabilities. So let's look at this in code. Again, we're going to start by defining our placeholders, and the inputs to the model don't really change. All that's changing is the internals of the model. So our placeholders are exactly the same. You have your x values, and those are, again, going to be 128 examples at a time, and each example has 784 pixels. And then we have our labels, or our y-trues, and those are also going to be 128 by 10, because it's 128 examples at a time, and each example has 10 possible values. Here we get to our parameters and operations, and the code looks pretty similar to before, but instead of having only a single m and a single b, which we apply to the x and pass through softmax, we have two sets of m's and b's, so two sets of parameters. The first set, we apply mx plus b to, and we add rel to that, and that is the output of our hidden layer. And then we take that hidden layer and we pass it into the next set of mx plus b's, and we apply, and that gives us our y prediction. Now our cost function is the exact same as before, and as you notice, we're still using the softmax cross entropy. None of the code here has changed. And we come to the optimizer stage, still using gradient descent optimizer, same learning rate, still trying to minimize the cost, so the code here hasn't changed. And finally, we get to the train code, where we construct our session, and for 2,000 iterations, feed in examples from MNIST in order to minimize the cost. This code hasn't changed either. So what I would like to really call out here is that with TensorFlow and these kinds of higher level machine learning primitives, we're able to rapidly iterate on our code, adding an extra whole hidden layer and converting our logistic regression into a neural net only required a change of 3 or 4 lines. So before we look at the accuracy, I'm going to just say that I'm not only going to monitor the test accuracy as we did before, as in before we were only evaluating the model's accuracy on examples that it hasn't seen before and hasn't trained on. Now we're going to monitor those, and we're also going to monitor train examples. So how accurate is our model at predicting the examples it already has seen before? So let's check it out. We're getting 97% test accuracy and 97% train accuracy. Wow, that's pretty good. We were getting 92% before, and with 20 lines or so of code, we're able to convert these squiggly, hard-to-read, handwritten images into accurate predictions, and we were able to solve some basic OCR tasks. And we're getting that with only 3% error. But we don't want to stop now. We want to try to squeeze out those extra 3 percentage points. And how do we do that? Well, we have to go deeper. And to go deeper, we're going to add another hidden layer to our model. So no big surprise here. We're going to be using the same building blocks we used previously to construct a hidden layer. You have an M parameter, a B parameter, a nonlinearity, and instead of only having one set of those hidden layer blocks, we now have 2 sets. So the inputs come in, they apply to the first hidden layer. The result of that gets passed into the second hidden layer, and the result of that finally goes into our classification layer. Let's see this in code. So, since all the code, aside from the model, remained unchanging, I thought it would be good to just show what the change in the model was. And it's actually pretty small. Instead of having 2 M's and 2 B's in one hidden layer, we now have 3 M's and 3 B's. The extra M and the extra B correspond to the additional hidden layer that we defined. And I also kind of wrapped it up in a little function to kind of encapsulate the code. And we now see that we have a neural network with 2 hidden layers in TensorFlow. And again, only 3 lines of code have had to change. So if you're wondering, how is this model doing? Okay, so we're getting 97% test accuracy. So that's no improvement. but now we're seeing 98% train accuracy. So essentially what this means is that our model has not learned a generalizable function that extends the data it hasn't seen before. It's gotten really good at predicting examples it's been able to train on, but these kinds of predictions don't generalize to examples that it hasn't yet seen. And this is commonly referred to as a problem with overfitting. Overfitting can occur when a model is over-parameterized. It has too many parameters, and using all those parameters, it can essentially learn a really complicated function that might be super good at solving the task it's already seen, but is not so good when new challenges are presented to it. And you can kind of see that from this training curve, where our cost on the training data continues to go down as we feed more and more data to it. But for the data it hasn't seen before, the cost is no longer going down, which essentially means that it's not able to learn anything general enough that it can extend to unseen data. So how might we solve this? Well, I'm going to dive into one of the hidden layers and give us a little view into what exactly is going on. So imagine we're inside a hidden layer. Our inputs come in as the x values. The connections kind of represent mx plus b, and the y is the result of the hidden layer. And as you notice, each of the lines from x to y represents one of the activations that comes into our network. And since our model is over-parameterized, the technique we can use to kind of fix up this issue is something called dropout. So dropout forces the model to learn more general representations. Essentially the way it works is each of these connections, which represent the activation of one of the parameters that we set, is stochastically set to 0 with a given probability. So if I set dropout to 50%, that means that 50% of the time some of the activations will get set to 0, and the rest of the time the activations will just continue on through. And essentially this forces our model to learn more generalized features for how to operate on the data. And it's kind of like thinking about building a really complicated code base that's super tightly coupled. Sure, when you're done building it, it works on the problem that you're currently trying to solve, but as soon as you try to extend it later, the code totally falls apart. So you have to go in, you have to decouple your system. You can't allow the parameters to rely too heavily on each other. Likewise, in our neural network, dropout is going to improve how good our model is at generalizing by essentially forcing each of the parameters of our model to learn a more general way to represent the data that we're feeding into it. And let's see this in code. Well, this looks pretty similar to the code for two hidden layers neural networks that we saw before, except in the light purple, you see that we added a little bit of dropout, and we use the built-in tf.nn.dropout operation. So instead of just taking our hidden activation 1 and passing it into the hidden activation 2, we first apply dropout to the hidden activation 1, pass the result of that to hidden activation 2, then we take the hidden activation 2, apply dropout, and pass that into our output. Now, the interesting parameter about dropout is the peak keep value. So this says what the probability of keeping an activation as is should be. So, when I have my y pred equals model x 0.8 in the second to last line, that means with an 80% likelihood, keep any given activation, otherwise set it to 0. But when we're evaluating our test accuracy, we don't want to be using dropout because we want our model to essentially use all the information it can get. So at test time, I'm going to construct an additional model where I'm going to set dropout, the dropout peak keep to 1, which means that 100% of the time keep all of the activations. And that's just like the standard 2-layer neural network at this point. So let's see how this might look. Again, the diagram is pretty similar to how it was before. We have our first hidden layer, our second hidden layer, and our classifier layer. And the only thing that changes is we now apply dropout to the result of the first hidden layer and to the result of the second hidden layer. And I'm sure we want to know how our model is doing. Let's see. Okay, we're getting 98% test accuracy and 98% train accuracy. So 98% of the time, we're taking those squiggly handwritten digits with just like 20 lines of code, we're able to convert them into their actual digit. So we could keep going and try to eke out, those extra like 2 percentage points, but I think you guys get the idea. TensorFlow makes it very easy to build neural networks and to train them, it's not a problem at all. But now I want to tell you guys about just some of the general tips and tricks of building models in TensorFlow, so when you build your own, you won't run into the same kinds of problems. So the first tip I'm going to give you guys is about scaling predictions. So let's go all the way back to the logistic regression model for MNIST that we defined. Again, we have our placeholders, our parameters, and our operations. And you might be wondering, well, we applied softmax to the result of mx plus b, but we didn't write softmax anywhere in our code. In fact, our cost function looked like the top one, where we simply call tf.reduceMean of the cross entropy on our prediction and on the true label that the input should have been. But really, shouldn't it have looked like applying the cross entropy to the softmax of our prediction? Well, actually, TensorFlow cross entropy operations, they apply the softmax for you under the hood. So if you were to apply softmax on your own when you feed it into the cost function, you will actually not get your model training because it's as if it has had softmax applied to it twice. And this trick really trips up a lot of people. I've probably been bitten by it a dozen times. So the real thing to just keep in mind is that when you're doing your cost functions using the built-in TensorFlow costs, pass in unscaled predictions, don't scale them first. Okay, the next trick we're going to be talking about is parameter sharing. So when I built the neural network with Dropout, remember I had a train model that had 80% keep probability, and I had a separate test model that had 100% keep probability. But there's actually a small subtle bug with this code. Let's see what I'm asking TensorFlow to do. So in the top, we have the 80% EP keep model, and in the bottom, we have our 100% EP keep model, dropout neural network. The issue with this is we've essentially told TensorFlow we want 2 separate models with their own parameters. So the first one has its own version of M0, and the second one has its own version of M0. And that means that since we were only training the first model at test time, the model won't actually be able to make accurate predictions because it hasn't been trained. It has its own set of parameters. So really what we want is something more like this. Here, we've actually linked up the parameters from the train model and the test model. So that way, when we train, we can use the parameters that we've learned at test time. So how might we do this in code? Well, instead of just calling ypred is model x0.8 and ypred test is model of x1, we first have to construct a variable scope. So this is kind of like the context that our model is being defined in. And then we just have to tell TensorFlow to reuse variables. So now TensorFlow knows when I see M0 for ypred, it's the same M0 for ypred test. So that means that the parameters should be shared. Now, if you remember in our 2-layer neural net, we have our hidden activation 1, we have our hidden activation 2, and our function only returns our output. Well, let's say I was curious about my hidden activations. I wanted to perhaps plot out the norm later, or just kind of look at what the activations might be. One way I could get them out is I could return them from my function, my def model function. But that kind of pollutes what the function is. The function is no longer just my model, it's my model and my activations. Or perhaps I could store them in some global state, then we have global state pollution issues. The good way to do this in TensorFlow is to use the collections. The collections are essentially these buckets that you can drop anything like parameters or operations or model predictions into, and then access them for later use. So in this case, I want to store my activations. So in my first line, I'm going to create a collection called activations. and I'm going to put h1 into it. And in the line after, I'm going to add another parameter, or like another operation to my collection of activations, and I'll give it h2. Now later, I can go in, I can tell TensorFlow to get the activations collection out, and I can actually inspect the values later. Now I have nice, clean model code, and when I want to introspect it later, not that big of a problem. The really nice thing about these collections is that there's actually a bunch of built-in ones that TensorFlow manages automatically for you. So a great one is the Trainable parameters collection. Essentially, when you define a model and you configure your parameters, TensorFlow will do the bookkeeping for you such that any parameter that's going to be trained in your optimization step will be saved for later use. So now at any point, I don't have to worry about tracking all my parameters. I can just grab them out at any point, tell it, pass it into the session.run function, and access the parameters for later use. No problem. And one final trick I want to tell you guys about is some stuff involving placeholders. So if you remember, initially, when we defined our MNIST placeholder, we had to give it an explicit batch size. We said, this model only works if I'm feeding 128 MNIST examples at a time. But this is actually kind of a problem, because suppose we were to deploy our model into a production setting, a user might send 5 or 6 images, and that's only 6 images, it's not 128 images, so our model is queued. What we can do instead is set our batch size to none in our placeholder, and now this allows TensorFlow to be flexible. Whenever it sees a none in a placeholder, it knows that that will be set at runtime, and it can accept really any shape along that dimension. So for example, if I were to have some nice code here, I have my placeholder, my model, my cost, and my optimizer. And first I'm going to be grabbing out batches of 128 at a time, and then maybe later I'll be grabbing out batches of 512 at a time. And since I set my placeholder as having a batch size of none instead of 128, TensorFlow can keep chugging along, no problem. So that's all my tips and tricks. And for the final part of this chat, we'll be talking about some advanced TensorFlow and how we can build our own recurrent neural networks for image generation. So first, a little bit on recurrent neural networks. Suppose we were building an image classification, a sentiment classification model, and it would take in text like the food at the restaurant was very good, and maybe it wants to map it to the sentiment, so it'd give a 1, because that clearly has positive sentiment. We could do this with one of our straight up, 2-layer neural networks, no problem. But the issue is how we're going to represent this kind of sentence. We could pack it into a TF-IDF vector. We could figure out, a bag of words model, something like that. But all of those kind of ignore the sequential nature of sentences. Like when we look at sentences, we're not looking at the whole sentence at once and then converting it into some, bag of words model in our mind. The order matters of what the words come in. So what we really want to do is look at the words in a sequence. So this means instead of the food at the restaurant was very good, all at once, we're now treating our input as a sequence of words. The 0th element of the sequence is the first element is food, and good would be the 7th element of our sequence. And this is where R is really shine. Instead of operating on fixed size data, they can operate on sequential data, and they'll look at an element like they'll make some sort of prediction, then they can look at the next element, food, make some sort of prediction, and the nice thing is the prediction of food has now been conditioned on the prediction from the. So when we look at, we'll make a prediction there, but that prediction will be conditioned on food and the. So when we finally go to the end of the sentence, our model has learned some sort of internal representation of the sentence in a sequential manner. So here's kind of a good way to think about it. We're going to have multiple time steps through our sequence. So T0 is the, T7 is good. And at each time step, we're going to operate on that element of our sequence, generate some output, look at the next element of our sequence, so T plus 1. And we're also going to take the previous output, so the output from T0, and use that to generate our output at T equals 2. So here's kind of like a little diagram of it. So this is the general equation for a simple RNN. In the simple RNN, you still have your nonlinearity. This one, uses tanh instead of ReLU. Then we have our mx plus b. But if you notice, mx plus b is operating on x, our input at time t, and it also has some sort of input for the output of the model at time t minus 1. So when input comes in, it is operated on, gets shoved out, and that output is combined with the next input of our sequence to form the following output, and so on and so forth. So in standard TensorFlow, this is kind of what it would look like. You would construct a placeholder, but instead of just being batch size by feature size, so like 128 by 784, it has to have 3 dimensions. The first dimension is your sequence length, the second is your batch size, and the last is your feature dimension. So this would be 28 element long sequences with 128 examples at a time, and each example has 28 features. Then I would get the built-in basic RNN cell that comes with TensorFlow. I have to set the shape of the cell as well as the first parameter of the cell is like how many how many hidden units it's going to have, and the second is the sequence length, and then I'm going to call the RNN cell on our input data in order to get the outputs that the RNN is processing on. This is good, but it's not super flexible because let's say, for example, I want to support sequences of a bunch of different sizes. Now TensorFlow has ways to handle this, but none of them are particularly particularly elegant quite yet. And maybe I want to have some sentences that are 7 words long, some sentences that are 100 words long. So I want to build a more general RNN, and the only way to do that is to build it yourself. So how are we going to do that? Well, first we need the magic of scan. Scan is a special operation in TensorFlow. It takes in a function, and it takes in a sequence of elements. And for each element in the sequence that you pass in, it computes some operation as defined in the function, outputs that, and then for the next element of the sequence, it gets the previous output and can run some operation on that with the current element of the sequence to generate its next output. So here I do a little example with a cumulative sum. Our elements are a list, 1 through 6. Our step function is simply saying output each element plus added to our previous output. So when I call scan, first I see the 1. The 1 comes in and I output it. Then I see the 2. The 2 gets added to our previous output, which was 1, giving us a 3. Now I see a 3. That gets added to our previous output, which was 3, giving us 6. Then I see 4. That gets added to the 6 in output, and so on and so forth. So you can really see how scan aligns pretty closely to how we define the neural network. An RNN. You feed in an input, you have some sequential nature to your input, and then at each time step, you take in an input and the previous output, you use that to generate your next output. So here's how we might build an RNN with scan. So remember our RNN equation at the bottom. That is what I'm going to put into my step function. So we have our nonlinearity, which is tanh. Then we're going to apply mx plus b to x and our m and b parameters. And then you are going to apply mx plus b to the previous output from the RNN, as well as you have a separate set of RNN parameters that apply only to the previous output. And that's how essentially you can write your own RNNs using scan. And what's really cool about these kinds of models is that we can use them for stuff like sentiment prediction, but since we're always predicting an output at the next time step, given our previous time step, they can be used as generative models, which means we can run them in a generation mode. So imagine, I'm trying to do some task like generate a sequence of words that sounds like some famous person. I might have my RNN output the first word that they might say, and then using that first output, feed that back into my RNN in order to generate the next word that they might say, feed that output back into the RNN, generate the next word they might say until I have a full sequence of words. So a pretty cool task that I defined, I just kind of came up with it for this talk, was MNIST generation, where the task is you fed an MNIST digit, maybe it's like a squiggly 6, and you want to generate its complement, where the complement is 9 minus its value. So for example, if I fed it a 7, I should generate an image of a 2. If I fed it a 1, generate an image of an 8, and so on and so forth. And you might be wondering, these MNIST digits, how do we represent them as a sequence? So the way I did it was I took each digit, I split it up into a sequence of rows. So since they're 28 by 28 images, each row has I have 28 rows with 28 pixels in each of them. And that's how I kind of convert my MNIST digits into a sequence of row images. And to train this model, what we're going to do is we're going to take in the first 27 rows of the MNIST digit, and we're just going to try to predict the rest of the complementary digit. So it'll first see the start of the 6 up to the last row, and then using that, it's going to try to predict the whole 3 image. And in order to then generate images out from this RNN, we'll run it in generation mode, where we simply take the first row, we feed the RNN the whole 6 sequence, and we have the first row of the digit it's trying to generate, and based on its representation of the 6, it's going to try to output the next row of the 3, takes that output, feeds it back in, and tries to generate the following output of the 3 until we finally have a full 3 defined. Now we did this all with a a single RNN. Let's see how the generations look. Okay, they don't look so good. So essentially what happened is the model was trying to do too complex of a task. We're trying to force a single recurrent neural network to understand what the images are, generate some sort of internal representation, and then do the whole task of being able to generate its complementary digit. So to solve this, I split up the task into 2 discrete stages, and this is called sequence-to-sequence modeling. So first we take the input, and we have an encoder RNN. The encoder RNN would take something like the 6, looks at each element of the 6 sequence. Then we take the final state from that sequence, so that was the state that has been conditioned on all previous rows of the 6. And we use that to start kicking off the decoder phase. The decoder is its own RNN, and all it's responsible for doing is trying to do the prediction of the 3. So again, we iterate over the 6, we grab the final state, which was conditioned on the whole 6, pass that into our decoder, and now we start trying to generate out the 3. So here's kind of what the code looks like. It might look kind of scary, but at a high level, all it's doing is we're going to be setting up a encoder RNN where we pass in our sequence of inputs. Then we grab out the final state, so that's a state that's been conditioned on the whole input sequence. We pass that into our decoder, and our decoder is going to be generating our output images. So we're all wondering what this might look like, and show you, here are the generations from our MNIST complement sequence-to-sequence model. The left side were the original images, and the right sides were the generations. So essentially what this means is our model was able to look at a 6, understand what a 6 is, understand how to do like the subtraction or the mapping into the complement, and output those pretty clean looking complementary digits. All right, so that is the end of this introduction to TensorFlow. Thank you guys all for coming, and I'll be sticking around for a Q&A session after.